So while Dan goes off and finds our next presenter who's lost, I'll cover one of our next presenters. I'll cover for Anna, who is just unfortunately sick with a horrible fever. So I hope I can do this well. I did see her give a practice version of the talk, and so it's not all new to me, and she has sent me a bunch of notes, but forgive me if I stumble a few times. Okay, so bringing up the slides. Good. So this presentation will focus on extreme weather events, concentrating on their impacts on corn and soybeans because they're the dominant crops here. So we had Anna really concentrate her research on those, and historic and projected changes in these extremes in eastern Ontario. Climate change is having an impact, of course, on the frequency and severity of extreme weather events such as heat waves, droughts, high-intensity storms, and flash floods. As their frequencies increase, extreme events are expected to adversely affect crop yields and increase the vulnerability of agricultural producers to climate change. Although most agricultural areas routinely cope with extreme weather events and their impacts, ongoing changes in the frequency and distribution of these events will make more areas exposed to climate extremes. We commonly think of weather extremes as catastrophic events causing devastation to natural and man-made systems. So like I said earlier at the start of this series, it is often the less dramatic ones that can cause significant effects on crops. Unfavorable conditions during critical crop growth stages can result in dramatic yield losses, even though no records in temperature and precipitation have been broken. In other words, the rest of society may not even have noticed that there was an extreme event. So the general idea behind Anna's approach was to look at the crop's growth curve and identify the most vulnerable periods during its development, as well as the extremes that could potentially be damaging to a crop in these periods. So here in this slide, in the example for corn, we can see that it is susceptible to flooding in the early vegetative stages of growth. Then drought takes over as the problem. Drought is the problem in key reproductive stages such as pollination. And then later on, frost becomes the problem in later stages of grain filling before harvest. So Anna did a thorough literature search to find, what are all these critical stages and how to parameterize them for corn and soybean in the region. So again, the study area, looking at eastern Ontario, but looking at what weather stations were available in the surrounding region as well. Spatial and temporal analysis of observed changes in the phenological extreme indices was conducted using data primarily from 6 weather stations representing eco-districts located in the study area. Using weather station data as opposed to the gridded climate data made it possible to avoid issues such as reduced signals of extreme events known to occur during the averaging and interpolation of weather data. That said, we are also in the process of getting gridded versions of the weather data into our modeling frameworks so that they are available for analysis and visualization. But for this analysis, we're concentrating on really cleaned up, standardized data from 6 specific locations. So we started with all the locations available in black dots here as weather stations that exist during the record, but if any of you have ever actually tried to use weather data, you run into problems of some data being available here for this time period. This station over here is great, except that it was gone for 5 years and things like that. Lots of stations get shut down is a big problem in Canada as well. As a result, where am I in these notes? We take advantage of the fact that weather station data for temperature and, to a lesser extent, precipitation are representative of much larger regions. So one station from each of the eco-districts was selected to serve as a representative station in the analysis. In cases when historic records of the weather station in the eco-district were shorter than 30 years, a representative weather station was selected from a neighboring eco-district. So you can see the couple examples here where the red dot is just slightly outside of our study area. The analysis of extremes is sensitive to the presence of missing values. Therefore, infill data sets for minimum and maximum daily temperature and precipitation data series for selected weather stations were produced by Dr. Harold Schroeder, following the methodology discussed in Schroeder et al. 2000 and 2008. So he produced data sets for us through a collaboration that he has with, I believe it's the Ontario Ministry of Natural Resources, that cover two 25-year periods and has divided them up. Sorry, that's supposed to be up now. 1961 to 1985 and 1986 to 2010, just for purposes of easy comparison. For future projections, we use the high-resolution downscaled daily temperature and precipitation data that is available for the same ensemble of 12 models that I mentioned before that's been sort of pre-screened to those ones that work best with extremes. They were identified that way in this model intercomparison project, CMIP5, and we are using the ones with the RCP 8.5 scenarios from the GCMs from 2011 to 2035. The reason for that time period, there's less certainty in model projections the farther you go into the future. We kept getting feedback that the near future is more relevant to the farmers, therefore we just focus on that 125-year period. In the rest of this presentation, you'll see spatial maps and graphs, and the maps, we struggle with. We want to use the ensemble model, show the variability, but then it gets really hard to visualize them. So for the purpose of this presentation, you'll see some graphs that show multiple GCM outputs, and then the maps are all done using one specific model, the MPI ESM model that is closest to the centroid of the entire ensemble. So the idea of putting those into those maps was there isn't a specific known bias to extremely dry, wet, or hot conditions, but we are doing this for all the rest as well, and we'll keep working on other visualization possibilities. Okay, to develop the relevant indicators, literature reporting crop tolerance to extreme wet, dry, hot, and cold conditions at different phenological stages of corn and soybeans was collected and reviewed. The sources included books, peer-reviewed articles, agronomy reports, and technical papers by government and non-governmental organizations. Temperature and precipitation threshold data for different phenological stages were extracted from literature along with yield loss percentages associated with exceeding those thresholds. Extreme events resulting in potential yield losses of at least 20% were considered. So that led to a list of possible indicators, and through further analysis, we chose the ones that got built into the Envision system that we've been talking about. So for corn, based on literature search, 8 indices were identified and calculated. Interestingly, all of them showed up both in the past and the projected series. The difference between the ones that are now highlighted in green and red is that the green ones occurred less than 3 times in the study subperiods that we examined for this region, and they weren't chosen for any further temporal or spatial trend analysis. But the ones in red occurred in all or in almost all of the years, and they're discussed further in a future slide. For soybeans, 11 indices were calculated. Unlike corn, there was a large number of extreme events that are potentially detrimental to soybeans, according to work done elsewhere, but they were not recorded here in any of the past or projected data, and so they now are the ones that are showing up in black. One indicator, the one that's green here, occurred only once, and the other ones that are in red were the ones that were taken for further analysis. So in these figures that show maps, any of the 2 columns on the left are they're based on historical data. The one on the left, that's really testing my glasses, is 1961 to 1985, and then the middle column there is 1986 to 2010, and then the one on the right is the same indicator calculated on the forecast of that MPI circulation model. So in this one, we are looking at springtime weather extremes for corn, poor seeding conditions, and early flooding. So poor seeding conditions on the top, early flooding on the bottom. And the specific definitions of those are in those tables that showed up earlier. We can see that there has been and there's expected to be some spatial variability with a slight overall increase in the number of weeks with poor seeding conditions over time. Early flooding conditions have increased significantly in the last 25 years, particularly in the eastern part of the region where most of the agricultural lands are located. In the future, according to this particular model, there will be somewhat less of the early flooding, with the eastern ecodistricts experiencing wetter conditions than the western ones. Some implications of increases in the wet conditions during the plant season Dan's already showed you some great pictures, but includes planting delays and potentially the need to switch to a different crop if the planting window for corn, which needs a higher amount of energy than soybean, is missed. And that's occurring all over the place in this region right now. Yield losses of 7% per week are assessed for seeding delay, and plant death due to early flood, if it's submerged for over 48 hours, obviously results in 100% crop loss. Okay, these were added later, and I don't think I have notes, so see if I can wing it. This is showing the same indicator, so poor seeding conditions for over time. And if Dan remembers, was that a specific weather station or average of the weather station? Probably a specific weather station. I think she said it when we went over these, but we'll say it's a specific weather station. It might have been the Ottawa one. It doesn't say it here. So the blue line across the first 2/3 of the graph, I guess, that's the historic conditions. So you can see there's a lot of variability. But in general, a relatively low number of hectares affected, with a couple big exceptions. And then when you get into the GCM predictions for the area, I'd say, actually she then filters out so you can see a little better. With the 3 that are bolded, she took one that shows very, very, very low variability overall, so it's obviously not looking for a whole lot of problems with seeding, so lower moisture. One that seems to be sort of showing a pattern very similar to status quo conditions, what we're seeing in the past few decades, and then one that's showing a lot more variability and some really bad years in terms of seeding conditions. Next category, dry conditions, overly dry conditions. Corn is sensitive to dry conditions, if you remember from earlier in the presentation, mostly during the reproductive stages. Pollination drought has the most severe implications and can lead to up to 50% loss of yield. So that's very important. Blister stage drought, which is the bottom series of maps, can cause 20% decreases in yield. So in this region, we see that while pollination drought shows a consistent decrease over time in general, blister stage drought seems to be becoming more prevalent, especially in the southwest of the region. Next is milk and dough stage drought, so just further along in the phenological stages of corn, and they're generally considered to cause 20% decreases in yield if they hit past the threshold values, and we can see a distinct increasing trend in both those indicators in eastern Ontario. Moving on to soybeans. Planting conditions are becoming more variable and generally wetter, particularly in the eastern part of the region, with increases of almost 2 weeks in some eco-districts. Here, for soybeans, a 2-week delay in seeding is not as bad, I guess, because they can deal with a shorter season, but it can still result in up to 8% yield reductions, and 4-week delays are considered to result in a 15% yield reduction. And finally, the impacts of not enough moisture on soybeans. Mid-season dry conditions have been variable in the past, but are expected to increase substantially in the next 20 years. Drought during later reproductive stages has been increasing, but the projections show a change in this trend over the region, with the exception of Ottawa. The pod filling drought and the seed development drought can potentially result in yield losses of over 30%. Okay, so thanks, Anna, for putting that together. We're sorry sorry, Anna, that you're sick, and we're sorry she couldn't be here to talk about them. But this is probably the most documented part of it, in that she's got a thesis out and papers coming out soon, and we've got stuff available on the website. If you have questions about that, we'll do our best to answer them. Any questions or comments? Yes, UI.
Did you look at crop heat units and trends in that?
Yes, but to set the background context. It was calculated, and she used it to help characterize the region in the beginning, but a large part of what we were looking at was, okay, that's one of those sort of real aggregate things that masks the impact of extreme events, and she was concentrating on pulling out new extreme indicators to supplement that information.
No, it's just that we know our seasons are delayed. That seems to be showing up in the historical data. But at the
Yeah.
end, our falls seem to be...
Were you here when I first began this morning?
No, sorry.
So that's we've got that slide. It's just
Okay.
right there it is. So that's for the same data over the same region. We've got growing season length and crop heat units.
Okay.
So we wanted to pull out the more nuanced information about the impact on growth state.
Thanks.
Well, okay. No other questions or